Now let's resume chapter 7. We are going into 7.2 of our textbook, by the way. In the previous video, we went through various examples of sampling distribution. Here's an example of a range distribution, and it created an outline of a histogram like this, skewed to the left. Clearly, this was not normal. This is an example of a frequency distribution, rolling a die a number of times. We have a uniform distribution kind of like this. Clearly not normal. But in some cases, we do have normal behavior. As you can see, something like this. We are looking at the sum and the means. The blue is the sum and the pink is the mean, and they're both exhibiting normal-like behavior. Are they really normal? Well, it'll turn out to be yes. But exactly what kind of normal is it? Because if you are to use the normal distribution, you have to calculate the z-score. For that, you have to know rather the mean and the standard deviation. You see, z is x minus mu over sigma. That was this formula we used over and over again in chapter 6, wasn't it? Well, the central limit theorem here, this one, will answer that question. By the way, this is not a precise statement of the central limit theorem. It's just a naive description of it, but it'll do for our purpose. Let x be a random variable with the mean mu and the standard deviation sigma. Then, for sufficiently large n, the average distribution of n repetitions of x can be approximated by a normal random variable with the mean mu and the standard deviation of sigma over square root of n. Let's see. This is a mean. X is a random selection. So if you select one element from the population, then that's x. Now if you repeat that n times, you get a sample of size n. If n is 10, then you're selecting 10 times and form a sample, and then take the average of that 10. So that's n is the sample size. Typically we use bar to represent the mean, so we use x bar. Now, what is the normal distribution which approximates this distribution of the means? Well, it has expected value of mean mu, and that makes a lot of sense because all these x's over there, everything in the numerator has the mean mu, so add the same mu n times and divide by n. I'm not surprised that I'm gonna get mu here. Now what about this one? Well, that's a little bit trickier to explain, but it'll turn out that way. And that makes a lot of sense, at least in qualitatively. You see, the common sense tells us that the bigger the sample size, the more accurate your sample study is, or more precisely speaking, the more confident you are about your point estimate. That's what the sample size does. And look at this. Sigma over square root of n. Square root of n is an denominator, which means the bigger the n value, the bigger the sample size, the smaller the standard deviation. Consequently, the more concentration around the expected value mu. And of course, if you take smaller sample size, which means square root of n is smaller, then we have larger standard deviation around the expected value, which means the more likely that your point estimate is relatively far away from the real value mu, real population mean mu. That makes a lot of sense qualitatively. Quantitatively, not just this new standard deviation becomes smaller as sample size increases, but also that it is proportional to 1 over square root of n. This is going to be the new standard deviation that you'll have to use for your z-score computation. Now, we are using not x, but mean of x, so you have to use x bar. So the numerator is not x minus mu, but x bar minus mu. And the denominator is also adjusted to the new standard deviation, sigma over square root of n. Typically, we use SE, the standard error, in place of this denominator. So please remember this. Z is x bar over mu over the standard error, and the standard error is sigma over square root of n. This formula is just a variation of the same z-score formula that we have been using, x minus mu over sigma, but in place of sigma we are using standard error, and depending upon the sample size we have standard error which came from the original standard deviation with appropriate adjustment. The adjustment here is sigma divided by square root of n. Depending upon the circumstance, we are going to use different standard errors actually. If you go over to chapter 9, chapter 10, and so on and so forth, you're going to have different standard error formulas, but this one will remain the same. At this moment, standard error is sigma over square root of n. That's the only thing that you have. So you can use this one directly, but personally I prefer you to use this one, and then standard error equals to something something, because this standard error may change later on in later chapters. Okay, let's do an example here. Let's go over to this example, example 2.3. Let x be a discrete random variable with a mass function p, which is given as follows. Let's see, this mass function is a little bit more complicated than rolling a die, because if you roll a die, then you have just uniform mass distribution because the probabilities was just all 1/6, but this time it's a little bit more complicated. How complicated? Kind of like this. The first probability when x equals to 0.5, it's 0.4, so that's the first height. And then the next height is 0.05, and the third height is 0.1, and the final height is 0.45. They all add up to 1. And this is the graph of the mass function. And in order to utilize this central limit theorem, you gotta know the mean and the standard deviation, and standard error will be the standard deviation over square root of n. Well, in this problem, use the central limit theorem to estimate the probability that the mean of 100 repetition of x exceeds 1.2. Basically, it is asking something like this. The mean of x mean of 100 repetition of x exceed 1.2 when n is 100. That's basically what you have to do. Okay, alright, let's begin. By the way, we already saw the mass function. Let's find out the others. Here is the mean of x. From this mass function, we can find out the mean easily. Probability times x value. Probability times x value. Just add them all up, and this is what we get. Mean is 1.3 something. Standard deviation, we just multiply probability times deviation squared, probability times the deviation squared, and so on and so forth. Add them all up, we get the variance, take the square root, and that's gonna give me the standard deviation. It just calculator works, so let's just take these for granted. 1.31 and then 0.69 something. Now, how do you find out the z-score? Well, we have all the ingredient. It's x minus mu over standard error, sigma over square root of n, and we were given 1.2, right? 1.2 minus the expected value of mu, and sigma, we calculated, this one, over square root of 100. It's all here where I just highlighted. Punch in your calculator and you get negative 1.623. And that's when you conclude that the probability you're looking for, probability that the mean exceeds 1.2, is equivalent to probability that standard normal exceeds negative 1.623, and, well, correspond to this kind of normal picture. Greater than 1.2 goes like this to the right hand side, and in order to find out the shaded area, we have to find out 1 minus of this left hand side where I'm showing my mouse, moving my mouse around, because that part corresponds to the shaded part of the z-table. Looking at the z-table, which I'm going to leave you, you're going to get approximately 0.95. Well, actually, no, excuse me. Looking up the z-table, you're going to get something close to 0.05, excuse me. Taking 1 minus of that, the final answer is 0.95, approximately speaking.